So I'm going to talk about, well, very similar to other talks here about digital tools for mostly for phenotyping and how this help genetic improvement of livestock. Okay, so genetic selection is extremely important in agriculture, plants and animals, because of we improve the efficiency of production and the quality of the production as well. And it is actually remarkable the genetic gain that we have accomplished in livestock and crop as well in the last few decades. There are two things that happen in animal breeding that really expedite things. One is the invention of mixed models and blood methodology that we can work, especially in livestock. We have these complex pedigrees, completely unstructured data and equal families overlapping generations, and selection is going on and so forth. So actually we can accommodate all this using blood methodology. And then more recently, with the advent of the genotyping technologies, we've been using genomic selection. So all these help with this genetic gain that we have accomplished in livestock. But now what are the current challenges is that there are some traits that are very difficult, expensive, or sometimes requires the sacrifice of an animal so that you can measure. And these are traits that are very important nowadays because of consumers' perception or requirement and social requirement. So people are interested in animal welfare, disease resistance, for example, product quality, for example, nutritional properties of meat and milk, and so forth. So that's where digital technologies can help. So I mentioned genotyping technology that we use, for example, trying to map genes, but also for genomic selection for prediction of phenotypes. And we can use many other omic technologies in terms of functional genomics studies, trying to understand how genes work, and maybe this information can help with prediction. But what I'm going to focus today is on this, how to measure phenotypes, okay? So I'm going to focus mostly meat animals today. I work across species, dairy cattle, beef cattle, pigs, and poultry mostly, and fish a little bit also. And today I'm going to focus on meat animals, okay? So we are using sensor technologies, things that we can use to look at motion of animal, sound, for example, to detect like disease, like animals coughing, for example. So that's, well, we saw examples today with GPS for tracking animals. Said sound we can use for detection of disease, temperature, same thing, chemical composition for food quality, for example. So, but we've been doing many using digital technology in many different ways, but today I'm going to focus on feed efficiency. Okay, so we have the input, that is the feed, and output could be milk, could be eggs, meat, any other animal product. So it is not too difficult to measure the output, like milk yield or weight of animals. But using this technology, we can, for example, monitor weight on a daily basis, for example. We can look at body composition also. So we use digital technology to help measuring the output. But then this is very tricky and difficult, is to measure feed intake or feed consumption in an individual basis, because animals in general are raised in groups. So you know how much the group is eating, but not individually. Okay? So this is an example where we are using mid-infrared that is very common to look at the composition of milk, but here actually we are using the infrared spectroscopy to predict feed intake in dairy cows. Okay? So that's an example. I won't have time to go into details, but I'm going to show examples of applications, and then we can discuss, or you approach me afterwards to, if you're interested in discussing any of these examples here. But we had 300 cows. This was performed here at the University of Wisconsin, so we have this electronic gate, so we know exactly how much each animal ate. And then we had the milk samples from those cows. And then we had a strategy of data dimension reduction. And then we compare different models. So the traditional models use the milk yield of the cow, the body weight or metabolic body weight, that is body weight power 0.75, and the days in milk, so stage of lactation. So that's how you predict the feed consumption of an animal. But of course, this is an average for the animals on that specific condition. So we want to look at animal-to-animal variability. So then we compare models using the infrared information with all or features or the selected features and so forth. And then I don't need to go into details, but the infrared information did improve the prediction of feed intake of cows. Okay? Well, cows we have, for example, in Wisconsin, they are mostly in barns, and we have silage that we offer to the cows. But another very important, and was mentioned today here also, is to monitor animals that are grazing. Okay, so this is a small example that we run. Details are in this paper here, and we are interested in expanding this. But this was just to classify animals, or each time if the animal is grazing or not grazing, and we use accelerometer. So you have accelerometer attached to the neck of each animal, and then it's very simple, it's very clear the difference when animals are grazing because of the movement that they have, or when they are not grazing, ruminating or resting. Okay? So we use different machine learning methods, different cross-validation techniques, and this is very important. And quite often people do cross-validation just by at random splitting the data into training and testing, but quite often you overestimate the prediction ability, because when you move from you develop a tool and then you apply this to animals in a different farm or new animals, so the quality of prediction is not that good. So what we did here was to use, like, leave one animal out or leave one farm out, so to see how the prediction quality changed. And we don't need to go to details, but we compare the model, different models, generalized linear model, random forest, and neural nets, and then the different cross-validation strategies. Okay? Very good. So that's trying to estimate feed intake. So let's look at the growth of animals now. And we are using computer vision, mostly in this kind of approach. And we was mentioned today here, different kind of cameras. We use RGBs, especially for dairy cows, where we can recognize animals by the coat color. And we use 3D cameras as well for estimating body weight. I'm going to skip this. Some of you discussed different technologies of depth cameras and different tools that you can use depending if you are just interested in classifying pictures, if you have or you don't have an animal, or if you want to segment, find locate animals in image and so forth. So one example here with pigs. So with people try to develop a nutritional, precision nutrition. So you need to know the body weight of how much animals are growing, so you feed appropriate diet in the amount and quality of the diet. So, but measuring body weight is very time consuming, it's stressful to the animals. It's basically impossible with pigs. They are noisy, they don't like to be touched. So the idea is to use cameras to do this. So we had an experiment with 650 animals. We had information on body weight and 2 body composition traits, muscle back and back fat, that we measure using ultrasound. And then we had kinetic cameras capturing these 3D images. So we developed a pipeline that is automatic. So you have pictures, you automatically classify pictures where you have an animal or not, and then you need to select those images where animals are in a good body position, like straight body, not touching the wall. And so that's a picture that is not good. This is a good one. And once you select a good one, then you take the biological features like length, width, volume, area, and so forth. And then we develop models using different machine learning techniques with these biological features, and also a deep learning approach where we just feed the image as input. Okay? So the models work fine. Actually, the deep learning was the best one. Very good prediction ability, let's say, like the square of the predictive correlation. It's very good for the body weight, not so good for body composition. So you may need larger sample sizes and maybe try some different approaches here. Same thing we use for beef cattle. So these are beef cattle in feedlots. So we have a system with RFIDs. So animals, when they approach the water tank, we have antennas that read the RFID. So you have the ID and the ID of the animal. And then the RFID, the antenna also triggers the camera. So you capture images, and the image and the ID goes to the cloud, to the central computer and to the cloud. Okay. So the images are again select, so you classify, select good pictures, and then you process them, and you get very good correlation with the body weight. So these animals were in pens where we had electronic scales inside the pen, so the animal passively goes through the scale. So we had multiple measurements of the body weight and multiple pictures, and then we estimate the body weight in different time points of their life. So again, we compare different models, for example, here, neural net, partial least squares, last, and so forth. Very good. So this is the R-square again, cross-validation, very high cross-validation. But again, so in this case, we have one single feedlot, so one group of animals in the same diet, the same location. So again, I want to say this is good, but to predict the body weight of animals in this kind of condition, or if you go to a different breed, different diet, things are going to deteriorate. Okay, so you need to retrain the model with additional data. And lastly, with an example with fish here. So we want to select, genetic improve, in this case, tilapia for the fillet quality. So of course, this is something that you can measure only after you harvest the fish. So we had this trial here with 3,000 fish with pictures, and we measure they were harvested, so we have carcass weight and yield in each fish. Okay? So we develop a deep learning approach. So this was trick to get the body, the whole body separate from the tail and fins. And this is the publication where you can get more details, but again, was very successful. So overall, we see computer vision as a very promising tool in livestock. not only phenotyping for selection, but for management as well, because with one single picture or one single camera, let's say, you monitor multiple animals and you can monitor many different things. You can monitor behavior, how they interact with each other, aggression, body weight, skin lesions, and so forth. So I think it's one of the best sensors, like multi-use, that you can have. So this is a little bit of results. Intersection over union, so trying to locate the body of this fish, and the depth of the deep learning models that we are using. So just to conclude, digital technologies, we have been used a lot in terms of research, and we see they are coming to the field as practical tools. As the cost goes down, we have many tools that are we need to adapt them to be able to use in farm conditions where you have the weather, we have animals trying to get the cameras or sensors. So you need to adapt these tools to be able to use with livestock, especially in outdoor. And then we have all this challenge that were discussed here in terms of data transmission, data storage and management. And of course, we need to develop models that are able to handle this high dimensional data over space, over time. And like I said, it's useful as high-throughput phenotyping for genetics, genomics, and selection, and also in the context of precision livestock farming, as it was mentioned here. Okay, so people in genetics using high-throughput phenotyping are maybe helping indirectly precision livestock farming, and individuals working in management and developing tools for precision livestock management, they are also helping high-throughput phenotyping for genomic selection. Just to mention, so that we can use these tools to measure new traits, things that we couldn't measure before, or we can use these tools to measure traits that we've been measuring, like body weight, but now in a high throughput, like real-time setup. And then we can also have indicator traits. So now you can maybe measure things that are related to disease resistance, for example, and you are able to select indirectly for those traits that you are interested in. Just to finish acknowledging some, well, my group, I forgot to list here, my own group, and then the examples that I'm showing here these are the first authors. So João Dória is a professor in my department, colleague of mine. Arthur is a former student that works for COB now, and these are two former students as well that are doing their PhD. They developed their masters. What I showed here was part of their masters, and they are doing PhD now. And funding from this, from USDA mostly, and University of Wisconsin. And these are companies that we work together. So beef cattle from DSM, pigs from the PIC. Okay. So thank you very much, and I'll be happy to answer any question.
So very impressive, Dr. Rosa. I just have a very quick question about the accelerometer. So I see we have some experience for the acceleration data before, and we have found some shortage of the sensors. So the battery lines of the sensor is very short, and we kind of we just have a specific periods of the during life production cycles. I don't know how you adjust that.
Yeah, so what we had here is 15 days, and it was in a research farm in a university, actually in Brazil. This was conducted with a collaboration with a group in Brazil. So yeah, what you're saying, I mean, there is this long way from research to application, right? So many things that we can do in a in a research setting is not directly applicable. So we have internet available, you have technicians that know what they are doing available, we have electricity available. Now, when we go to feedlot, for example, we need to use solar panels. We need to use radio transmission because we don't have Wi-Fi. It's far from the central computer. So yeah, so we need to. I don't have the answer to you because we didn't work with the accelerometer for a long time. But for sure, you're saying it's a big task, like going from a research setting to a commercial application.
Okay. Thank you.
Yes.
Talk to us about that.
Accelerometer.
About the cyber infrastructure for these kinds of projects.
Any other question?
Tanya Berger-Wolf, Ohio State University. My question is as you mentioned, that for every setting, you had to, the big assumption is that they have the same kind of diet, the same kind of conditions. So what is the effort going into training these models and getting the annotations and data and calibration versus the generalizability of these models and these approaches?
So two questions, how we deal with the generalizability and how we annotate?
Well, combining those two, the big promise of computational approaches, just let's say big computer vision or more generally machine learning, is that they're less invasive and that you don't have to, put that much, and they're less time consuming. But for that to hold truly, you need to estimate the effort that's going into training, getting training data and calibrating these models versus the trade-off of that versus generalizability to other settings, other diets, other species. Yeah. So do you have any estimate on?
Yeah, no, each case is a case. For example, for the pigs here, we had like 3 genetic lines, and we had males and females, and 2 main age groups. So we did the whole thing. We tried to train the model in 2 genetic lines and see how you can predict a 3rd line that you didn't see before. Look, males and females. And in this case, was interesting that with deep learning, if we have males and females in your training set, and if you had the 3 genetic lines, you don't need to inform the model the sex of the animal or the line, so that the model capture all that. So this was interesting. So, but with beef cattle, we saw that there are 2 major groups of beef cattle: the Indicus and the Taurus, Taurine. And we saw that when we train the model with this breed that we use here, there is an Indicus, and we try to predict the body weight of Angus, for example, was very poor. So then we need, so if I'm developing a model for the feedlots in Brazil and they have mostly this white cattle, that's fine. Now, if I want to use the same tool in feedlots that have Angus or other breeds, you probably need to retrain, or we showed in this case that yes, you need to retrain with new breed.